Okay. Just tell me if you can see the whiteboard, huh? Can all of you see the whiteboard?
Yes, sir, it's visible.
Okay. Okay. Now can you see the PPT?
Yes, sir.
Okay, great. Okay, so this is the first problem. This is your class test problem, the module 3 problem. Okay. So I hope all of you remember this problem. Hello? Do you remember this problem? In case no, just take a look. In case not, just take a look. Hmm. Yeah. Can all of you see this? Hello?
Yes, sir.
Yeah. So let's now solve this this particular problem. How will you solve this? So what's the problem? This is the class test problem. So what's going on here? How will you draw this game tree? So first is the incumbent, who is the firm who is already present. So what does he do? He chooses either to behave innocently or to be strategic. Correct? Correct?
Yes.
Now, all of you see the whiteboard, I hope. Now the entrant, oh God, why do people enter so late? Now, the entrant, what can the entrant do? Which I think we should just hang on for a minute. So many people joining in now. So what's the entrant doing? The entrant can either stay out or you can enter. Correct? Yes or no? Hello? Debojyoti, can you hear me?
Yes, sir, you are audible.
So now what are the possible actions for the incumbent? The incumbent can either fight or share. This is your class test problem. If the incumbent is strategic, then also the entrant has two options: to stay out or enter. If he enters, then the incumbent has two actions. What are those two actions? Fight, share. Do all of you agree with this? This is what it is? Hello?
Yes, sir.
Now the payoffs are given in this manner. If the incumbent is innocent and the so being strategic has a cost C. Being strategic has a cost C. What is being strategic? This is like giving a threat. It's like giving a threat that, see, behave yourself. It's that kind of a threat. Don't enter, behave yourself. I hope all of you can see the whiteboard. Ayushi, can you see the whiteboard?
Yes, sir, I can see it.
Okay, great. So now if the incumbent is innocent, he behaves innocently, and the entrant stays out, which means nothing has happened. The incumbent retains his monopoly. So he gets a payoff of, let's call it pi m, and the entrant gets a payoff of 0. Okay, so let me use another ink maybe for this. So you have pi m comma 0. Okay. Now, if the entrant enters, then what will happen? If the entrant enters, then what will happen? Well, the incumbent can either fight or share. If he fights, then the payoff of the two parties are. And if they share, then their payoffs are given by pi d, which is pi duopoly. And this W stands for war. Let's say. It's going to be exactly the same here, just that incumbent has already incurred a cost of C. So if the incumbent behaved strategically and the entrant stays out, the incumbent again has monopoly here, but he has already incurred a cost of C. So his payoff will be pi m minus C, comma 0. Okay. Now if the entrant enters and the incumbent fights, then it will be just that it's identical, just that the incumbent's payoff becomes lower by an amount C.
Sir, the question mentioned that the strategic cost C is included in the war, so will not incumbent cost also be pi W?
Sorry?
The question mentioned that the strategic cost C was included as a part of the war cost in
Was
pi
it
W.
mentioned?
So, yeah.
As a part of the war cost?
Yes, it is given incumbent's investment under strategic behavior is assumed to be part of total welfare.
Total welfare, exactly. Not part of war cost. It is part of total welfare.
Okay, so it will be deducted from the
Absolutely, right?
final war.
That's correct. That's correct. That's correct. Okay. Now see what's going to happen. Let's say if the incumbent behaves innocently. Let's say. Then what should the entrant do? What should the entrant do? If he stays out, then he gets a payoff of 0. If he enters, then what should the incumbent do now? If the incumbent is standing here, what should he do? Should he fight or share? Well, there is a inequality given over here, which is pi m monopoly is greater than duopoly. This is given. So should the incumbent fight or share?
Share.
Share. Okay. So the entrant knows that if he enters, the incumbent will share. So then what will be the entrant's payoff? The second payoff, pi d. If he stays out, then what will be his payoff? Tell me. 0. So standing here, what should the entrant do? Stay out or enter?
Enter.
Enter. Okay. So if the incumbent chooses innocent in the first step, then this path will be followed. This. Got it? Clear? Is it clear?
Yes, sir.
Okay. If the incumbent chooses to be strategic, then what will happen? What should the entrant do here? He can either choose out or enter. If he enters, what should the incumbent do? Should he fight or should he share? Which is more, pi w minus c or pi d minus c?
Share pi d.
Share. Now, what should the entrant do? If he stays out, he gets a payoff of 0. If he enters, then pi d minus c. Well, it's implicitly assumed that c is less than pi d. So the entrant should enter. Correct? Hello.
Yes, sir.
So if the entrant enters, then the incumbent will share. So if the incumbent in the first stage chooses to be strategic, then this path will be followed. So what should the incumbent do at the starting? If he chooses innocent, then this path is followed and he gets a payoff of pi d. If he starts being strategic, if he starts threatening, then there's a cost to threatening, then this is the total payoff he gets, pi d minus c. So what should he do?
Innocent. He will behave innocently.
He'll behave innocently. So this is your subgame perfect Nash equilibrium. This, then the entrant choosing enter, and then the incumbent choosing share. Got it? This should be your subgame perfect Nash equilibrium. Is it okay? Hello?
Yes, sir.
Okay, good. So that's your first problem, let's say. Now let's look at another problem. Look at this problem. Very easy one. Read it. Read the problem. This is problem 1. So how should we do this? How should we do this? Can all of you see the problem? Hello? Can all of you see problem 1?
So what does reservation payoff signify?
It means that, so what is this? Here you are saying, I want this much. And so let's say you and I are playing this game. We are making quotes, how much we want. We are making demands. I want X, you're saying I want Y. Of course, you will want more than what your reservation payoff is. That is, this much you definitely want. That is given by X naught. Okay. So let's say that is 0.000.
Reservation payoff.
If you want.
Okay, so below reservation payoff, I will not get any
utility, let's say. Utility, let's say.
Utility.
Okay. Right. Okay. Okay. So the reservation payoff is like a lower threshold. Let's say it's like 0.0001. Okay. Now, how should you solve this problem? How should you solve this problem? Wait. Can all of you see the whiteboard now?
Yes, sir.
So how will you solve this problem 1? How will you solve this problem 1? So the thing is, what are your quotes? They're x, y, such that x should be greater than equal to x naught. Y should be greater than equal. These are your reservation payoffs. And x plus y less than 1. Right? Less than equal to 1. This is what you mean by a feasible pair, xy. Correct? So if both of us end up quoting a feasible pair, then we get x and y. If we end up quoting an infeasible pair, then we simply get our reservation payoffs. Got it? Then we simply get our reservation payoffs. Hello? Clear? So you're dividing something of size 1, let's say a cake of size 1. So the total payoff is size 1. And you're dividing it between the two of us. That's the game. Do you see this? So you have something, let's say 1 rupee, $1. which you and I have to divide. And our reservation payoffs are 0.001 and 0.002. Now the question is, how do we quote? Let's say I quote 0.5 and you quote 0.6. Will that be a feasible quote? Will that be a feasible pair? Ayushi? No, right? Because 0.6 plus 0.5 is not less than equal to 1. Got it? So now, what is the set of, what will be a Nash equilibrium then? These are our strategies. What should be the Nash equilibrium? Well, if I quote X, how much should you quote? Well, you quoting anything, exactly, 1 minus X. You quoting anything less than 1 minus X is stupidity. Because you can increase your quote till 1 minus X and still be feasible. Isn't it so? Isn't it so? And for you quoting 1 minus X, X is my best quote, best response. And these are, of course, subject to the constraints that my X should be greater than equal to X naught. And your 1 minus X should be greater than equal to Y naught. Correct? Do all of you agree with this? Any quote of this format, any pair of this format is thus a Nash equilibrium. The total size of the price is $1. If I get X, if I quote 0.3, you quoting anything less than 0.3 is stupidity, right? You should quote all the rest. Do you see this? Hello? Devajyoti, is it clear?
Yes, it's clear.
Now, what does this tell you? What do the constraints give you? So X should belong to X naught 1 minus Y naught, right? So any quote of this format such that X belongs to X naught 1 minus Y naught is a Nash equilibrium. Correct? Got it? Hello?
Yes, sir.
Good. Good. Now let's go to the next problem. Look at problem number 2. Take a look at problem number 2. Okay, a very simple game. So you have two companies, Panasonic and Zenith. Okay, they are producing TV. If both of them enter the market, then they fight with each other and they end up losing $40 million. If one enter and the other does not enter, the entering firm gets 250 and the non-entering firm gets nothing. If both of them don't enter into making TVs, both end up getting nothing. Is that okay? Is that okay? Hello?
Yes, sir. That's
Perfect. So now think about it. So let's go to the whiteboard. This is problem 2. So how will the payoff look like? So you have Panasonic and you have Zenith. What are their strategies? Enter, not enter. Enter, not enter. Right. If both of them enter, what will be their payoff? Minus 40, minus 40. If Panasonic enters, Zenith doesn't enter, then Panasonic's payoff is 250, 0. Panasonic doesn't enter, Zenith enters, 0, 250. If both of them don't enter, 0, 0. Is it clear? Hello? Hello.
Yes, sir.
Okay. So now let's find the pure strategy Nash equilibriums. How will we find this? If Panasonic enters, what is Zenith's best response? To not enter. If Panasonic doesn't enter, then what is Zenith's best response? To enter. Right? Also, if Zenith enters, what is Panasonic's best response? To not enter. If Zenith does not enter, what is Panasonic's best response? So you see, we have two Nash, pure strategy Nash equilibrium. Correct. Do you see this? Hello.
Yes, sir.
So these are my two pure strategy Nash equilibrium. Now, if I ask you what are the two mixed, is there a mixed strategy Nash equilibrium? So what will be your answer? Well, you know how to solve that. So let's say P, Panasonic, is playing a mixed strategy alpha 1 minus alpha. Alpha is greater than 0. And Zenith is playing a mixed strategy beta 1 minus beta. Okay, where both alpha beta belong to the open interval 0 to 1. Correct? Correct? Isn't it so? Hello.
Yes, sir.
Yes, sir.
Now, how do we solve for this? Let's say for Panasonic, given that Zenith is playing this mixed strategy, beta 1 minus beta, what is Panasonic's payoff if he plays E? What is his payoff? Well, with probability beta, he will get minus 40. And with probability 1 minus beta, he will get 250. Right or wrong? If he chooses
Yes, sir.
no enter, then what will be his payoff? Well, with probability beta, he'll get 0. And with probability 1 minus beta, he'll get 0. That is 0. Now you know that if Panasonic has to, okay, let's see. If this is greater than 0, then he'll always play E.
So if Panasonic not enters and it Zenith enters with beta, it should get 250. Right?
No. What is Panasonic's payoff? If he's not entering,
Oh, okay. Yeah.
it's always 0, right?
Right.
Now, if this is greater than this, if this expression is greater than 0, this expression, then he'll always choose to enter. If Panasonic always enters, then Zenith will also always enter. Sorry, Zenith will always not enter, and we are in this equilibrium. If this is less than 0, then he'll always choose to not enter. If Panasonic chooses not enter, then Zenith will choose enter, and we are in this equilibrium. Okay, so if it is greater than 0 or less than 0, we go to our pure strategy Nash. We get back our pure strategy Nash. Right? So what is the only other option which hasn't been explored when both are equal to, when this is equal to 0? That is 250 minus 29 beta, sorry, 290 beta is equal to 0. That is if beta is 25 by 29. In that case, Panasonic is indifferent between playing E and NE, right? If he's indifferent between playing E and NE, then there is a possibility that he's going to choose an alpha greater than 0. Right? Why? Because now if he chooses an alpha greater than 0, then what is Panasonic's payoff? Well, with probability alpha, he chooses E, then his payoff is 0. and with probability 1 minus alpha, he chooses any, then also his payoff is 0. Got it? It's never negative. So it is rational for him to randomize between E and N. And this is the beta, 25 by 29, which will make it rational for Panasonic to randomize. And we are trying to find an equilibrium where both the players are randomizing. And that randomization is possible, is rational, only when beta is 25 by 29. Similarly, you can find the expected payoffs of Z given this mixed strategy which Panasonic is playing. And then you're going to find the alpha, which makes randomization of zenith rational. Got it? Huh? And this alpha 1 minus alpha, comma, beta 1 minus beta will constitute my mixed strategy Nash equilibrium. The beta you've already found, 25 by 29. Just find the alpha as well in a very similar manner. Is it clear? This is exactly what we did in that goalkeeper penalty shootout example. Is it okay?
Yes, sir.
Okay, great. What is the second part of your question telling you? Let me go back. It is telling you that if, let's say, the US government is giving a lump sum subsidy to Zenith and tells the CEO of Zenith that just enter, okay, just enter. You will get a subsidy of $50 million. Then what will be the pure strategy Nash equilibrium? Let's see. Then,
so the normal form representation of the game is same as the payoff table.
Yeah, that's right. The sequential form is called extensive form. Normal form means the table. That's right. Simultaneous move game. Enter, not enter. So what was the initial payoff matrix? Remember, it was minus 40, minus 40, 250, 0, 0, 250, 0, 0, right? This is what it was initially. Now I'm saying that the US government has decided to give a subsidy to Zenith if he enters. So what will happen? If he enters, just enters, he gets a transfer of 50. So what will be the payoff if both enter? Well, Panasonic will get a payoff of minus 40, but Zenith will end up getting a payoff of minus 40 plus 50, which is 10. In this case, 300. Right or wrong?
Yes, sir.
Yeah. Okay. Also, now this remains the same. If he doesn't enter, there is no question of subsidy. So these payoffs remain the same. Now, what is the only Nash equilibrium? Now we get one Nash equilibrium. See, if Panasonic enters, what is Zenith's best response? If he enters, he gets 10. If he doesn't enter, he gets 0. So he'll choose to enter. If Panasonic doesn't enter, well, then of course he'll choose to enter Zenith. Right? Which means Zenith will always choose to enter now. And if he always chooses to enter, then Panasonic will always choose not enter. So now, not enter, enter becomes my only pure strategy Nash equilibrium. Do you see this? So if the US government gives this subsidy to Zenith, Zenith becomes extremely optimistic and he always enters. Okay, entering and fighting and losing also becomes profitable for him. So he necessarily enters. And if he necessarily enters, Panasonic gets intimidated and he never enters. Right? So we are stuck in this unique Nash equilibrium now. We had two, remember? When there was no subsidy, we had two Nash equilibria, this and this. NEEEN, right? But with the subsidy, we just have one. Is it clear? All of you?
Yes, sir. Yes, sir.
Great. Very good. Let's look at another problem. Okay, read this problem carefully. Take 2 minutes, read the problem. This is problem 3. Read the problem carefully. Give me a minute. I'll just get myself some water. Is it clear? All of you? Hello? Hello?
So what does the inputs signify here?
Hmm?
The X1, X2, the inputs of each boat. What does this signify?
Input signifies how much each boat is spending.
Okay.
Okay. How much each boat owner or each boat is spending for catching fishes or crabs in this case. What is the expenditure? What amount of resources is one particular boat applying? Got it? So what could be resources when you're catching a fish? Well, you have this fish food which you throw, right? And you wait for the prey to catch on. So that's what you mean by the inputs. Clear? So that's the total amount
Yes,
of resource employed by one particular boat. That's X1.
So also, why isn't y equal to summation of all yi's?
No, capital Y is simply the total amount of resource, which is why should it not, why is it not the case? Because the number of fish is constant in a particular place, right?
Right.
So the amount of resource which is being spent in the entire, let's say, pond or river, that will determine how much is being caught, how much fish we are getting. Not the summation of the individuals, right?
Okay. Okay. Yeah. Got it.
Got it. Anyway, so now let's get back. Okay, so now what is this ith boat's payoff? Tell me. What is the ith boat's payoff? Well, the total payoff is given by, correct? But the ith boat ends up getting xi by x. That's what's given. That's the total revenue. The ith boat is getting this fraction of the total revenue. That's his total earnings. And what's his total cost? CXI. Correct? Do all of you agree with this? And this capital X is simply summation xi. Yes, Debojyoti?
Yes. Sir.
So this is what? This is simply A minus BX into xi minus CXI. Right? So this is AXI minus B xi into summation xi minus C xi. Or in other words, A minus C xi minus B xi into summation xi. Correct? Do all of you agree with this?
Yes, sir.
So the ith Both's payoff is a function of his own investment xi and also what the other guys have chosen, right? All the other x's are there in this summation. So now we are in a game theoretic scenario. My payoff is also dependent on what you do. So what should the ith board do? Well, the ith board should maximize with respect to how much he spends xi, how much resource he applies. So that is given by what? A minus C xi minus bxi into what is del xi summation xi? Well, that's simply 1 minus b summation xi into del xi, which is simply 1. Correct? Do all of you agree with this? Do all of you agree with
Sir,
this?
A minus C, only A minus.
A minus C. That's correct. That's correct. This won't be there. That's correct. Correct, isn't it, sir? So now if you just take a look, how will this look like? So this is simply A minus C minus 2bxi minus b summation xj, j not equal to I. This is 0. Isn't it, sir? Isn't it, sir? Hello? Hello?
Yes.
Yes, sir.
Okay, great. Now, if that's the case, now you know that all the boat owners are symmetric, right? They have the same cost C, which means in Nash equilibrium, it'll be xi star will be simply some x bar, let's say. Okay. Now, if that's the case, then what do you have? A minus C minus 2b x bar minus b into n minus 1 x bar is 0. Correct? Yes or no? Yes or no?
Sir, are we assuming everyone will have the same investment in it?
Yes. Why are we assuming that? Because everybody has the same C. A and B is also the same for everybody. So everybody is
Okay,
same. Everybody is faced with this equation, right? Everybody is faced with this equation. So there is no reason
Okay,
why.
had the C been different, then
Then it would have been different. Exactly. Then then the x size would have been different. So what is this? What is this x bar, which is everybody's choice? It is A minus C. If you take bx bar out, it's n plus 1, right? It's A minus C by b n plus 1, something like this. This is what every boat owner is choosing. This much of resource. Is that okay?
yes, sir.
Now tell me, if that's the case, what is the total amount of resources are spent on this crab catching? Every boat owner is spending this much or employing this much of resource, right? Then what is the total? What is the total x? It's simply n into this A minus C by bn plus 1. Right? This is the total amount of resource which will be spent in this Nash equilibrium. Right? . Do all of you agree with this? Hello.
Yes.
Okay, great. Now let's think about the following scenario, which is what the second part of the question is asking. Let's say there are these n boats, but we are assuming that they have individual owners, right? And they're competing. Remember, the revenue is getting divided xi by x, depending on how much resource you have invested in catching. Now let's say there is only one owner who owns all these boats, and he is deciding on how much resource to spend. Remember, the total payoff, the total revenue is ax minus bx square, right? So if all the boats are owned by one guy, he is only bothered about the total amount of resource which is being spent. He doesn't bother about how much boat I is spending. So what will be his objective then? He will simply want to maximize this. Correct?
So could you repeat this part?
So let's say you don't have these individual boat owners who are fighting. Why is there a fight? Remember, what is a boat owner I's payoff? It's ax minus bx square here. Remember, it was ax minus bx square. That's the total revenue into xi by x. Yeah, minus cxi.
Yes, sir.
So this component is what? This component incentivizes the ith boat owner to spend more, to get a larger share of this. Correct?
Yes.
Now, if there is a if there are no individual boat owners, but all the boats are owned by one guy, then he need not have this particular component, right?
Yes, true. Yeah.
Yeah. He need not have this component. So his payoff is he is simply bothered about the total amount of resource which is being spent, which is this minus cx. That's the total cost.
Yes, sir.
Then what will be that optimal total amount of resource? This a minus 2bx minus c0. So this optimal is a minus c by 2b. Now tell me, is this more or is this more? Which one is more? Is the total amount of resource employed in the Nash equilibrium more, or the total amount of resource employed when all the boats are owned by one guy? When is it more? When is more effort being spent? Huh?
If n is greater than 1, then x any is
Exactly. And of course, n is greater than 1, right? I mean, otherwise there is no problem. If you have just one boat, then the problem is trivial. So if n is greater than 1, that is if n is greater than equal to 2, then x ne is greater than equal to, greater than rather. Okay, which means that the total amount of resource which is being spent here is more than required for the total profitability of the business. And why is that happening? Because the individual boat owners are fighting amongst each other to get larger shares. Got it? Got it?
Yes.
So if you have a payoff between the total amount of resource, total payoff and this x, you have like a inverted parabola, something like this. So this is where you should be operating. But since the individual boat owners are fighting amongst each other, we end up getting here. Got it? Is it clear? So here this is a classic case where competition leads to a curse. Competition is a curse in this particular case. Is it clear, everybody?
Yes, sir.
Okay, very good. Just give me a second. I will